Anyone be willing to come demonstrate for the class? Anyone know how to do it? Basically from kind of a geometry problems. No? Anyone knows how to do it? Yeah, I'm going to mix it up because I think we've done enough algebra, a lot of algebra, right? So we're going to try to look at trigonometry because you guys need to have a good foundation for going into pre-calculus. That's the main focus of this course. So we're going to look at some trig. So, does anyone guess? This has nothing to do with area. So for those of you who thought about pi r squared, that's nothing to do with it. However, the area of a circle is pi r squared, right? Pi times the square of the radius, that's true. But what do we really want? We want to know the perimeter, all right? What's the word that they have for a circle? I think I heard you say it. What was that, Rihanna? The outside, okay. So it's got its own special word, the circle. The circumference? Sound familiar? All right, so the circumference of a circle is equal to what?
360.
No, 360 degrees? 360 degrees. Degree measure is a measure of the opening of an angle. Circumference is actually the distance or the perimeter of a circle. So C is equal to pi d. Look familiar? I hope it should look familiar. If not, it should be a review from however long back. So that's one way to write circumference. How can I write circumference in terms of the radius, which is what we're provided?
R squared.
R squared?
R times 2.
R times 2? Kind of get somewhere with the R times 2 thing, yes?
Is it something to do with pi? Is that R?
2R. No, nothing squared. 2R is what? 2R is D, so all you got to do is plug in 2R for D. And they just write it where they put the constants in front of the R. It'd be the same exact thing if you said pi 2R. Pi 2R, same thing, but they write it as 2 pi R. Okay? So either one of these formulas would give you the circumference of a circle. Bless you. D is the diameter. D is the diameter. If I had, let's say, this going on, this here is the diameter. That's what this D is referring to. The diameter is always twice the radius. We can write that the diameter is twice the radius. 2 radii make a diameter. Okay, so what would the answer be? If I want the exact value in terms of pi, the first part, what would it be? No. I want the exact value in terms of pi. I don't want a rounded decimal. How do you get it? You use this formula right here.
2R pi.
Again, I do not want to convert pi to 3.14 or anything like that. It's 2 pi. Good. If R is 1 mile, the circumference is 2 pi miles. And this is the only way to possibly express the exact circumference of the circle. Now, if I wanted a rounded value, then I would use the pi key on my calculator, which is going to have a little more accurate than 3.14. If I go out to however many decimal places programmed to go out to. So if I, on my calculator, I go 2 times pi, and I round it to decimal places, what would I get? see, if I do it on this calculator, if I go 2 times pi, 2 times pi, I get 6.2831, blah, blah, blah. And I want to round to 2 decimal places, so it would be 6.28 miles. And so you were right with the rounded value, but I wanted to hear the exact value first. I want to emphasize this fact of that pi is just pi. It's the only way to possibly express it perfectly is to write it as pi without doing some crazy limits or whatever.
So,
Yep, circumference is the perimeter. The circle is one of those shapes that's got it's a unique name for its perimeter, that's circumference. So now you know if there was let's say a yard or some sort of track or whatever, where you had the radius was 1 mile, which would be a crazy huge track. The distance, the perimeter of that circle is over 6 1/4 miles.
That's a huge circle.
It is.
Ew.
Yes.
I'm sorry. Does the book explain how to get the C equals 2 pi miles?
Does the book explain?
Yeah. Because like,
It would let 1 be r. A 1 plugging 1 into r, you have 2 times pi times 1.
Oh.
And how do you get that without using
How do I do what? This one? I use pi on the key on the calculator right here.
So the bottom one is the more simplified version.
The bottom one is the rounded value. The top one in blue is the exact value. Okay, so let's talk about pi because it seems to be the number that eludes a lot of people. Pi. What is pi? Let's start with there. What is pi?
1.1468.
No, it's not that. It's not. What is pi? Yes. It's not that either.
Are you just asking the definition of pi?
Yeah, because these numbers you're giving me, they're not. That's not equal to pi.
Oh, you mean what's equal to pi? I thought you meant like what is pi? Like pi.
Yeah, what is pi? Yeah. I'm asking
What is the number
is
of pi?
pi? Pi is approximately 22/7. It's approximately 3.4, but that's not what it actually exactly is. You could go out and you could write in decimal form forever and ever until the day you died, and you still wouldn't have pi.
So how about you tell us? How about you tell us what pi is?
Pi is not nothing. So if the circumference of a circle is equal to pi times its diameter, how could you write what pi is? How could you express what pi is? How could you rearrange that formula and tell me what pi is?
Pi equals circle.
Very good. Pi is equal to the circumference of any circle divided by its diameter.
That's what I'm about to say.
That's what pi is.
That's what pi is. Pi is the circumference of a circle divided by its diameter.
And pi is only a circle.
No,
So then why is it becomes of a circle?
but that's one definition of it.
So it changes its definition.
There are other ways to define it, which are beyond what we'll be studying. So for our case, we're going to look at just the definition of it being the circumference over the diameter. But I want you guys to also realize that 22/7 is an approximation for it, and so is 3.14, however far out you want to go, is also an approximation for it. The only way to write it exactly is to leave it as the Greek letter pi. So it's an irrational number. Irrational numbers, they go on forever in decimal form, and they don't repeat. There's no pattern to it. They have people that built supercomputers that did nothing but calculate the value of pi to like billions of digits, and even that's not the exact value of pi. Someone who either has too much free time, or someone who got paid to do it. Or both. Okay, so moving on. Today we're going to move on to chapter 5. We're jumping from we wrapped up basically chapter 1. We're going to look at chapter 5. Before that, we look at some trig. And the first section of chapter 5 is a good one: angles and radii. That looks like Radian.
Yeah, I was about to say that.
Let's clear that up a little bit. I should say radian. And radian.
There we go.
Measure. Okay, so most people are very familiar with degrees as the measure of an angle, but most people don't know what a radian is. And so our objective for today on the board is, what is a radian? Okay. If you have the textbook, this section starts on 481, and there's actually a nice little intro to it where they talk about modeling one's emotional status with one's intellectual status, one's physical status, and they can actually be modeled mathematically, and they have waves. So I'll read the opening of this. It says, have you had days where your physical, intellectual, and emotional potentials were all at their peak? Then there are those other days when we feel we should not even bother getting out of bed. Do our potentials run in oscillating cycles like the tides? Can they be described mathematically? In this chapter, you will encounter functions that enable us to model phenomena that occur in cycles. Graphs of functions showing a person's biorhythms, the physical, intellectual, and emotional cycles we experience in life, are presented in exercises 75 through 82 of exercise set 5.5. And here you see the presenting the opening where this person's mood seems to alternate, as most of us may have that. Days are better than others. Moods change throughout the days. If we go to exercise set 5.5 and we go to that specific exercise that they're talking about, and this will eventually get to this point here, you can see the waves of the graphs. Right? You can see the red being the physical, the blue the emotional, and the green the intellectual. And you can see they did a model where they have data that looks like they're showing it for about every 5 days. So they may have done something every day. And this is probably overall the average, these graphs here, yes. This is page 555. I just want to point out to you, that it is possible, depending on when you have functions that are going here, where you have both the red, the physical and the intellectual are both peak, but the emotional is on a low. And then you have another day where this person may have emotional peak, but the physical was not as strong and the intellectual was low. So you can have this occur when we have different periods for these graphs. And these are like the cosine and sine functions, which we'll get into eventually. But I just thought it was pretty cool that this chapter opened up with actually being able to, at least to a certain degree, model someone's intellectual, emotional, and physical states using math, which typically you wouldn't think that. So anyway, today we're going to look at, again, radians and degrees and converting degrees to radians. So why even have radians? If we know degrees can give us the angle measure, right? You can go, okay, 36.25 degrees. You kind of know how that opening is. Why even have radians? So, you have a question? Yes, please. Here's the main reason. Radians, who want to cooperate, radians give arc length. This is something that degrees do not do. This is why radians are, I guess you could say, advantageous over just degrees. You guys actually knew how to find arc length, but maybe didn't think of it like that. If we go back to where we started, you found the arc length of the entire arc of a full circle. And we said that the circumference is equal to 2 pi r. 2 pi radians is 360 degrees. And that's on one of the slides. 2 pi radians is equal to 360 degrees. And we can see that just from this formula right here, that P equals 3 pi r. So let's see this work out. The definition of a radian, according to the textbook, which is good, is 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of the circle. So what that means is if I could take this radius here, and I were to take that distance of 1 mile, and I were to curve it so it fits perfectly on the perimeter of this circle. So that distance is 1 mile. Whatever angle that makes from the endpoint of that arc to the other endpoint of that arc, whatever angle that makes, that is 1 radian. I'm not so much concerned about that knowledge of what a radian is versus the actual converting degrees to radians and understanding that radians can give you arc length, which we will look at on this slide here. So piece by piece, for a full arc, and I shouldn't say a full arc, but if you wanted to find the arc length of a whole circle, we use 2 pi r. 2 pi radians would be the central angle measure of a whole circle. This here, this S equals theta times R. What this says is this. S is arc length. Theta is the measure of the central angle, which needs to be in radians. And R is actually the radius. It's actually the length of the radius.
Is that an O?
It looks just like I have it written. It's called theta. It's a Greek letter. Like pi is a Greek letter, because a lot of the mathematics is coming out of ancient Greece. Back when they had no electricity and plenty of time to think about things like stuff like this. So notice here, I want you to see the relationship between here and here. Theta in this formula here is the 2 pi. Theta is the 2 pi, and the R is the R.
This says theta is measure of central angle in radians.
Yeah, it needs to be in radians, but we're not doing degrees. So if we we presented something information in degrees, we convert it to radians first and then plug it into this formula. And so, like I said before, 2 pi radians is equal to 360 degrees. And that's the conversion factor that we're going to use to convert degrees to radians. If we had to, radians to degrees. But typically you'll be converting degrees to radians. That's the more practical application of it. So this formula gives you the measure of any arc length. If you know the measure of the central angle and you know the length of the radius, you can find the arc length. So let's see a problem.
What does S stand for?
S means arc length. And you might ask, why use the letter S? Again, probably the Greek letter S is not the same S that we have for our alphabet. But S is just the arc length. That's the actual, the distance of, going along the perimeter of the circle. That's the arc length.
What's the central angle?
That is the measurement of the angle,
Oh, this is like this and
right?
part length.
Yeah, the arc length is this part here.
Yeah.
Yeah, we'll see a problem.
I know what you're talking about now.
Yeah. Alright, can I go to the next? Alright, so here's an example. Now, I know there's a lot on here, so let's just go ahead. Let's focus on just, try to ignore this over here. Let's just focus on what's circled in red as the example that I'm giving you. This is the information that you're given, what's circled in red. Okay? Actually, let me write that. This is the given information. You're given part of a circle, or a sector, and you know that the central angle is 45 degrees, which is typically how we always kind of thought about measurement of central angles in degrees. And I know that the radius is 50 feet. We're going to use that formula and we're going to convert degrees to radians to figure out the actual length of this curve, which has no turns, it has no edges, it is a perfectly smooth curve, yes. This is an S, and we're going to find S. So you guys will be able to find the distance of a curve. Okay, this comes about later. You can write it now if you want, but I'm going to show you how we get that. The given is just in red.
Oh, wait, so that thing over there is the mixer? Or no?
In fact, trust me on this, and just let me do this, and you'll see you'll see why.
Okay, I'm
So
sorry.
just no, it's okay.
I don't
You're
know
fine.
that hurts.
Questions are good, but I want you to focus on the fact that all you're given is what's in red. Okay, so let's first off, for us to use this for this formula right here, this has to be in radians. So let's go ahead and take care of that first. How do we convert 45 degrees into radians? Well, we said earlier that 360 degrees is 2 pi radians. And I'm going to use the degree symbol, and I'm going to use the abbreviation RAD to mean radians. Eventually, most textbooks, when they don't write the degree sign, it's assumed to be degrees. When they don't write RAD, and they have a pi involved in there, it's understood to be in radians. Okay, so here's how we do it. So if 360 degrees is 2 pi radians, I can write it as a ratio, and that's what I did right here. I want to convert 45 degrees into radians, and this is how I did it. I said, okay, 45 degrees times this conversion factor ends up being 1/4 pi radians. Okay. Now, why can I write this like this? Well, because this is a ratio. This is not a fraction. Let's be clear on that distinction: a fraction versus a ratio. If you guys remember, if I wanted the ratio of girls to guys in this classroom, I would count the number of girls, say 3, 4, 5, 6, 7, 8, 9. Count the number of guys, 1, 2, 3, 4, 5, 6. The ratio of girls to guys is 9 to 6, but the fraction of the class that is girls is 9 out of 15, the total. Okay? So there is a difference between a ratio and a fraction. I want you guys to understand that on a deeper level, because otherwise you look at this and I didn't explain that, you might think it's a fraction, and that's not what this is. This is a ratio. It's a direct comparison to values. I could have written this ratio as 360 degrees over 2 pi radians, and it would be the same ratio. Just like before I said 9 to 6, the ratio of girls to guys is 9 to 6. That's the same thing as me saying the ratio of guys to girls is 6 to 9. It's the same meaning. This is a ratio. It's not a fraction. You can put it either or. But here's my question. Would be, why did I write it this way and not the other way? That does matter for this particular situation. Why I wrote like this and not flip. Not because 360 is bigger than 45.
The degree. Is that why?
Yeah, the reason is, yes? That's the exact reason right there. We need to cancel out. I don't want degrees anymore. So degrees, you can think of this over 1, right? Technically,
Yeah.
over 1. The degree. Remember, you can simplify diagonally when multiplying ratios or fractions. You can simplify diagonally or up and down. I want degrees to go away. I want to be left with radians. So I have to write it like this. We're going to eventually find F. But right now, I have to have, this guy has to be in radians first for me to use that formula.
Are you about to make a ratio?
This ratio was made out of the fact that I know that 2 pi radians is 360 degrees. Now, if you look at it, you can tell that this simplifies to pi radians over 180. You could also use that one, which is a simplified version of it. That's the same thing. But I'm just going to keep it like this because I think everyone, the most practical understanding, because we all know about a circle and its circumference, that 2 pi radians is 360 degrees. So, degrees canceled. I'm left with radians. Now it's just a matter of, okay, the math that's involved. Okay, 45 times 2 is 90. The 90 and the 0 and the not, and the, here's the math. We just want to do it. You can also punch in the calculator, and you would get 0.255. So 9 and 36 have 9 in common, so divide by 9 to get 1, divide by 9 to get 4. So yeah, I multiplied 45 by 2 to get 90. So I have 90 pi over 360, and I'm not really focusing on, I know it's going to be radians, but just looking at the numbers part, remember that this is good to go over if you guys forgot to do stuff like this. The zeros, you can knock those out. That's like divide by 10. And then you have 9 and 36. 9 and 36 have 9 in common, so I divide the top of the 9 and the 36 by 9. Okay, yeah, so then the radians is here. I was just showing the calculation of the numbers.
How come you don't multiply the 45 by the 360?
How come I don't multiply the 45 by the 360? Hold on, I'm trying to get this thing to maximize out. Looks like it's not going to want to cooperate. Okay, so now it's acting real. It's acting real weird now. This isn't good.
It's the bottom thing. The black thing down.
Oh, I'm sorry. Thank you.
Wow.
This is a thing sometimes. Right? Now we had a glitch there. All right, so 1/4 pi radian. So 45 degrees is 1/4 pi radian.
How come you don't multiply by the top and the bottom? 45.
Oh, because 45 is 45 over 1.
Yeah.
Awesome.
What does that say? S equals 25 over.
Okay, so if you're at the end, S equals 25 has pi feet. So let's go step by step though. So here we have that 45 degrees is 1/4 pi radian. Did anyone still not get that part?
Oh, no, I got that part. I'm looking at it.
Okay, so everyone gets that. So then we're going to go over here. We're going to use our formula that the arc length of any arc is equal to the central angle measure times the length of the radius. And our central angle measure, which has to be in radians, is 1/4 pi radians. And R is 50 feet. And then just doing the math, you get 25 halves pi feet.
So really you just need the formula.
Okay, wait.
Yep, you definitely need this formula. Yep, yes.
How did you get, see? Oh no, that's the radius when you plug that in. So why do we have to do this over there?
I need to convert degrees to radians.
Oh, so that 1/4 pi is that little circle.
1/4 pi radians is theta. It is the angle measure.
So technically, we don't have to do any of that over there.
Technically we do, because in order for us to use this formula, theta needs to be in radians.
It's in degrees. You gotta change it.
That's the main point. So if we go back to the very beginning, radians give arc length. That's what makes them, advantageous over degrees. Degrees can't give arc length, but radians can.
Okay, go back to the other thing.
So
Okay.
plug it in and simplify. Yes. How we got what? Okay, so here 50 times 1 is 50 divided by 4.
Oh.
50 and 4, they both simplify, divide top by 2, you get 25 halves.
So that makes a lot of sense.
Now what we found, let's be clear on what we just found. We found the exact distance. We found the exact length of this arc. We found the exact length, 25 halves pi feet.
Okay.
So you use this formula to find any arc length.
We will have to ever check this.
Alright, so I want you guys to try one.
Oh, no.
I want you to convert 3 pi over 5 radians into degrees.